So welcome to the pre-lecture video for the next topic in the course, that of constant acceleration and free fall. And you should view this video prior to coming to class on the 5th of April. Additionally, you should read sections 2.4, 2.5, and 2.6 in our textbook, which is Holiday, Resnick, and Walker 10th edition. Pay attention to the learning objectives specified here to 13, 14, and 15 in section 2.4. Tell you have to know when to apply the constant acceleration model and states that you have to be able to apply it in appropriate problems. Section 2.5 addresses a very, very important special case, perhaps the justification for why we even study constant acceleration. We live in a constant acceleration world due to gravity, and all objects free fall, like the apple in our picture here to the right, with a constant acceleration of 9.81 meters per second squared downward. And then the last section, and pay attention to learning objectives 16 and 17, which says you have to be able to solve problems in the free fall constant acceleration model. And the last section is 2.6, graphical integration. Essentially, it tells you what to do when you don't have constant acceleration. We'll do it graphically, showing you how to find areas under curves to do graphical integration. But obviously, as you progress in your calculus courses, you could just learn to integrate analytically. So the learning objectives here are 218 and 219, and you'll find that they closely relate to learning objectives 214 and 215 from section 2.4. If you have any lingering doubts from our kinematics discussions last class, please go back and review definitions of position, displacement, average velocity and speed, instantaneous velocity and speed, average acceleration and instantaneous acceleration. You should be able to both give a sort of just a verbal definition as well as knowing the mathematical definition of these quantities. And I offer this to you as a kind of a memory aid in relating those quantities I talked about on the last slide, and we spoke of when we discussed kinematics last class. And I've kind of got in the center here descending position and displacement and the symbols for them, instantaneous velocity and change in velocity, and instantaneous acceleration. We'll talk about the average quantities here in just a second. But as you see on the left, as you move from position to velocity, what's involved, that's instantaneous velocity, is simply taking the first derivative with respect to time. And similarly, when you start with velocity and you move towards acceleration, you take the first derivative of velocity, instantaneous velocity with respect to time, and that gives you acceleration. And of course, hopefully you've progressed far enough in your calculus class to know that taking two derivatives with respect to time is the same as taking a second derivative with respect to time. You take the first derivative with respect to time, and then that result, you take its derivative with respect to time as well. That's what a second derivative is. So the second derivative of position with respect to time is acceleration. And if you want the average quantity, well, instead of taking a derivative with respect to time, and that's why I like this notation. I don't like some of the primed and dotted notation for taking derivatives. It specifically tells you that a derivative is a slope, a rate of change, in this case with respect to time. Just undo the limit as delta t went to 0. Make it the displacement over a time interval, and you get average velocity. Make it the change in velocity over a delta t, a time interval, and you get average acceleration. So if that's what you need to do on the left side, because you want the average quantities, just make a modification to my little memory aid derivative there. Now, what we're going to be studying today is this right side here, because we're going to start with acceleration. And of course, as we stated, it's constant. We're going to start with constant acceleration and integrate it and figure out a change in velocity, because an integral is an antiderivative, and so that should kind of make sense. And once we've got to velocity as a function of time, if we integrate it, that should give us a displacement. But before we get into calculus, I do want to show you a little let's call it a derivation of our model for constant acceleration. And no calculus is required here. I've used this when I taught an algebra-based introductory physics course. And the point here is when acceleration is constant, its average and instantaneous values are the same. So it's pretty straightforward to use what I just said on the previous slide, that average acceleration is a change in velocity. Remember, anytime you have that delta, that triangle, I think it's called NAMBLA is what the mathematicians called, I believe. It's always the final value minus the initial value. So it's the final value of velocity minus the initial value of velocity. And in our notation, initial value is always subscripted with a 0. Other references you might see might have subscript with an I for initial, or maybe for the final value might subscript with an F. Our text notation is the final value is just unsubscripted, and the initial is subscripted with a 0, I think to denote that the time is equal to 0 at that point. Because if you look at the time interval, delta t, in the denominator here, it is the final time minus the initial time, which we just make 0 by a convention. You don't have to. And if you look at other references, you might find T2 minus T1, for example, or T final minus T initial. We're going to use the initial time as 0, and that's why we're subscripting velocity as V0. All right, well, I've done this in one step here, and it's really about 2, maybe 3 steps of algebra, depending on how you do it. Obviously, you ignore the 0. You multiply both sides of this equation here by time, and then you add the velocity over to the left side of the equation, and we're left with the fact that the final velocity is equal to the initial velocity plus the acceleration times the time. Now, very, very straightforward, I hope, maybe even trivial. That's why I did it in one step. If your algebra skills are such that doing that in one step will cause you to make a mistake, don't do it in one step. Do each step at a time. Multiply both sides of the equation by 2. Add the initial velocity to both sides of the equation. Rearrange it as necessary. One of the things I think we tell students inappropriately is that they should be able to do things like this in their head. And the reality is, maybe after you've worked at it and practiced it for a while, but initially that may not be possible. You may need to write things out. This is reinforced by pop culture. One of my most favorite movies is Good Will Hunting, where Matt Damon, a South Boston kid who can't afford to go to college, works as a janitor at MIT. And he's on the midnight shift, and he solves a lot of math problems on the blackboards in the hallways that professors are leaving for their students just to challenge them. And he does it anonymously. And he's a math prodigy. And one time he's explaining to his girlfriend, played by Minnie Driver, by the way, how he's able to do math. And he makes the analogy to a German composer, I believe it was Beethoven. He says he just sees it. I mean, much like Beethoven, who could not hear the music because he was deaf, he just had to see it as it was sitting on the paper, what it would sound like in his mind's eye. Most of us don't do music that way. And similarly, Matt Damon claimed that's analogous to how he did mathematics. He would just see it. Most of us are not mathematical prodigies. And instead, we take more the Thomas Edison version of how we do mathematics, 99% perspiration, and then only about 1% inspiration. So don't feel because our textbook leaves out a lot of steps, like it does in showing you where equation 1 comes from, and why I did right here, that there's anything to be embarrassed about if it takes multiple steps to write this out. Now, once we've got the equation, though, you could see that velocity is a function of time. You might even say that all the parameters in a constant acceleration problem are parametric with time. You tell me what time it is, you give me the initial velocity and the acceleration. I can tell you how fast something is going out in the future based on those parameters. And I plotted what the velocity versus time is here, and hopefully your math skills are such that you recognize that velocity is linear with time with a y-intercept of the initial velocity. All right, so that's the first equation for constant acceleration in our model. How does velocity vary with time? Next thing we want to do, and it's a very similar pattern here, just a little more complicated, is look at what the average velocity is. Remember, we said that was displacement over a time interval. Final minus initial position. Again, x now is subscripted with the 0 to denote the initial position, divided by t minus t0. Rearranged in exactly the same way I did in the velocity equation. Multiplied by t, and then added velocity, the initial position to both sides of the equation, just rearranged a little bit. Excuse me. And I see that the position is equal to the initial position plus the average velocity times the time. Now here's the trick. Perhaps you have to recognize what the meaning of average velocity is here. Okay, and I guess if I look at a linear increase in velocity, it seems to me that the initial velocity added to the velocity any time later divided by 2 is going to give an average, right? 2 points, divide by 2. That's how you do an average. But if that's not immediately obvious to you, let's say in my curve here of a linear slope from V0, let's say that the initial velocity was 10 meters per second. And at the far right, at the very end, the final velocity was 20 meters per second. Well, hopefully in your mind you can go, well, starts at 10, ends at 20. Yeah, the average is probably 15, halfway in between. And that's exactly right. If I take 10 and I take 20, and I divide by 2, I get 15, which is exactly halfway, which is what this equation says. All right, well, let's take equation 1 now and substitute it in for the instantaneous velocity in the average velocity equation. And if you do that, you'll see in the parentheses, there'll now be 2 initial velocities, 2 times the initial velocity, plus the acceleration times time. And then there's a 1/2 outside the parentheses, which has to yet be distributed. And so that's what I've written over here on the left. Average velocity is equal to 1/2 twice the initial velocity plus the acceleration times the time. Well, our goal here, I may not have stated it, but our goal is to eliminate the average velocity. Okay, so I'm going to plug that right back into that initial equation that was just the rearrangement of the average velocity definition from last class. And once I do that and I distribute that 1/2, you can see that the final position is equal to the initial position plus, well, the 1/2 cancels the 2, the initial velocity times the time. Distribute the 1/2 again, plus 1/2 the acceleration times there's time twice, time squared. And so there's our equation. Our textbook likes to bring the initial position over to the left side of the equation, but x minus x0, x minus the initial x position, is equal to the initial velocity times the time plus 1/2 the acceleration times the time squared. If you're to solve that for the position, and as I said, velocity and position are dependent on time. They're parametric on time. You tell me what time it is later, I can now tell you what the velocity and the position is going to be. That's how we got to the moon, with that exact predictive nature of kinematics. But I hope that everybody recognizes if I'm to plot position as a function of time, it is quadratic. That curve is a parabola. And that's what equation 2 says. I should tell you, when I was an undergraduate, those were the only 2 equations I learned for constant acceleration. In fact, I was an undergraduate well over 40 years ago, and some of my professors were a little bit old school and didn't believe in equation sheets. And so we had to learn these equations, and I realized these 2 equations are the entire model. There's no problem I can't solve without equations 1 and 2. That said, though, I think there is a third equation that is very useful, which eliminates time. In this case, position and velocity are both functions of time. What if I want to know, say, velocity, if all I know is where the object is, what its position is? How do we eliminate time from these 2 equations? That's a little bit of algebra, but we could do it. The first thing I'm going to do is, in equation 1, I'm going to solve for the time. Okay, now it involves subtracting off the initial velocity, dividing through by the acceleration. Take a quick look at units. Yeah, that should be units of seconds. We'll talk about that when I do an example problem later. But now I have an expression for time from equation 1. And when you've got 2 equations and you want to work with them, take that time and plug it into equation 2, the one on the right. And I've done that, putting the expression we just got for time in parentheses. And, there's not much you can do with that unless you've got the gumption to go out and expand everything, because otherwise you'll never be able to simplify it. And so I did that. I distributed the initial velocity over the two terms in the time equation on the middle term there. And then I looked ahead and I said, well, acceleration in the denominator squared, that's going to be an acceleration over an acceleration squared. That's a 1 over an acceleration. So it's 1/2 with the a in the denominator, the acceleration in the denominator. And then I had to expand out the v minus v0 squared. Okay, and so I wrote those terms out. And then I had to distribute the 1 over 2 times the acceleration over the 3 terms in the parentheses set of the result from squaring v minus v0, squaring that term. And what I noticed, interesting enough, is I'm left with 5 terms now. And the first one and the fourth one are exactly the same, except one's positive and one's negative. So they cancel out. They add to 0, don't they? All right, next thing, if you're adding fractions, you got to get a common denominator. I'm not quite there because in that second term, I only have an acceleration in the denominator, so I need twice the acceleration, so I multiplied by 2 over 2. Multiplying by unity doesn't change anything. And now I have the ability to add these things up. And you look and you see that second term and the fifth term, they're very much alike, except for that factor of 2 now in the numerator. And that just makes the overall sum minus the initial velocity squared over twice the acceleration. And of course, the remaining middle term there, the velocity squared over 2a, that just stays by itself. And so I've come up with what's still over here, the displacement, x minus x0, is equal to the velocity squared over twice the acceleration minus the initial velocity squared over twice the acceleration. I saw the common denominator was in both terms. I multiplied both sides of the equation by 2a, and you can see that twice the acceleration times the displacement is equal to the velocity, the instantaneous velocity squared, minus the initial velocity squared. And now I've got a relationship, I call it the third equation. The velocity squared is equal to the initial velocity squared plus twice the acceleration times the displacement. Now, not necessary. You can always do that same bit of algebra with numbers if you just have equation 1 and 2. But over time, I've come to believe that equation is important. Oddly, we'll see it again later in the course when we talk about energy of motion. It's related to a concept called the work energy theorem. So just stick that in the back of your brain and remember this when we come to that topic later in the course. All right. So here's the review. My 2 equations, equation 1 and equation 2, written out so that it's very clear that velocity is equal to a function of time. Initial velocity plus acceleration times time. And position is also a function of time, only it's not linear, it's quadratic, it's parabolic. Okay? And those 2 equations can be combined to get that third equation there, which eliminates time. Is sometimes a handy way to get right to the answer quickly in a problem. And then I put the average velocity equation there, and that's a little bit of notation. I subscripted AVG, I think. Sometimes you'll see people subscript AVE for average. Another piece of notation you'll see in certain references is to put a bar over the quantity. And so that means average velocity. The final plus the initial divided by 2. And I included this graph of constant acceleration just to remind you, if you don't have this case where acceleration is a flat curve, none of these equations apply. Now, our textbook isn't satisfied with my 3 equations plus the definition of average velocity. It adds 2 more so that you can always go to a particular equation and just try to work it out with just one equation rather than having to do 2 or 3 equations to arrive at an answer. So in addition to equations 1, 2, and 3, which in our textbook are noted as equation 211 and 215, and they're actually in one of those pale green boxes. They're the most fundamental. After your author works through the equation for velocity eliminating time. So velocity is a function of position. Okay, that one is there as well. He adds two more. He doesn't tell you how he gets them, but if you look over on the right here, you can see that it just says displacement is equal to average velocity times time. Yeah, no kidding. But if you notice, missing acceleration there. So if you don't have the acceleration in a problem, that might be a quick shortcut way. I don't have this equation memorized. In fact, I've never used it in my entire physics life. Similar to the third one, you'll notice looks a whole lot like the second one, but if you study it carefully, you'll notice two differences. Instead of initial velocity, it's instantaneous velocity, and it's a negative sign instead of a positive sign with the 1/2 AT squared. Here are the curves, showing you these one at a time, but just in one place. And we're going to now shift over a little bit to some calculus, since you all have calculus as a prerequisite for this course. And I want to remind everybody, if you have that constant acceleration, you can integrate it, as I said, over time and get the change in velocity. And if you have the velocity as a function of time, you can integrate it and get the displacement. I went through that pretty quick. Now I'm going to get it a little more detail in the next slide. And because we're studying calculus, I want to make sure you see exactly how I get to this integration idea. I start with the definition of instantaneous acceleration. It's the derivative of velocity with respect to time. Again, I like this notation over the notation with the primes and the dots because I can work it like I do other algebraic expressions. I can multiply both sides of the equation by dt, the differential time. And so the differential velocity is equal to the acceleration times the differential time. And then the way to solve that is to integrate both sides of the equation. Now, when your author does this, they do it as an indefinite integral with a constant of integration, which has to be resolved using the initial condition that at time equal to 0, the velocity is equal to the initial velocity. And so that's certainly one way to do it, and I recommend you take a look at that. I like this approach, slightly different, accomplishes the same goal. I do definite integrals. Don't have to deal with the constant of integration. And you should notice the correspondence between the limits of integration on the time integral from 0 to t and on the velocity integral from the initial velocity to the final velocity. Now, the one issue I've created for myself with this approach is mathematicians don't like when your limits of integration and your integration variable are the same. And so what I've done is I've introduced v prime and t prime. They're referred to as dummy variables. Okay, and so when I integrate dv prime, what I get is v prime evaluated from the initial velocity to the final velocity, which is just the difference in velocity, the change in velocity. And when I integrate the acceleration times dt prime, I get acceleration times t prime from 0 to time, 0 to some time t, and that's just the acceleration times time. And hopefully you can see with just a little bit of rearranging, this becomes equation 1. Just bring the v0 over to the other side of the equation. All right. Hopefully no issues there. I will point out, I think, that one of the mistakes I see students make when doing integral calculus is to drop the differential. And I want to assure you that's wrong. I do understand some calculus professors, some mathematicians like it as shorthand, but not only is it required in a physics course, the thing to remember is differentials like a dt or a dv also have units, not able to be dropped. And yet you see people doing it all the time. All right, now let's move on to the next equation, what I called equation 2. Velocity, instantaneous velocity, is a derivative of position with respect to time in the exact same way. Multiply both sides of that equation by dt, the time differential. Okay, and then integrate both sides again from over the time, and I've introduced a dummy variable again, t prime, okay, which I had to put into equation 1 as well. It's acceleration times t prime. Limits of integration from 0 to t on the time integral, limits of integration on the position integral from initial position to final position. So do those integrals. Shouldn't surprise you that the integral on the left is just the final minus the initial position, the displacement. The first term is just a constant times dt. So yep, it's just velocity initial times t prime, value from 0 to t. That hopefully becomes trivial. Just v0 times t, the initial velocity times time. And the second term, well, the integral of a constant times time dt is 1/2 t squared. And you evaluate that from, that's t prime squared. You evaluate that from 0 to t, and you get 1/2 a t squared. Now, that gets us to what I called equation 2. The biggest single mistake I've seen people do in using equation 2 is forgetting to square the time in the 1/2 at squared. And hopefully showing you how the calculus of this worked. And since most everybody who takes a calculus course recognizes that a constant times time dt integrated gives you 1/2 the constant times t squared, you'll remember to square that time as soon as you see the 1/2, because you know the 1/2 is there because the integral of t dt is 1/2 t squared. You just have a constant here, constant acceleration. So this will hopefully give you some hook to hang on to the fact that when you write the 1/2, you'll remember that with the 1/2 must be t squared because you just integrated to get it. We'll talk about another technique here in a bit when I do the example problem on how to catch yourself if you make that mistake. All right, falling objects. Why do we do constant acceleration? Well, no less than Galileo proposed that someplace on the Earth, with no air resistance, a condition which he wasn't able to create, all objects fall with the same constant acceleration, 9.81 if you want to go to 3 digits, meter per second squared downward, and that's why we usually associate a negative sign with this. The symbol we often use is a little g for the acceleration due to gravity. Now, it's true that acceleration due to gravity is vertical, so it's often convenient to shift the constant acceleration equations that we just worked up in our model by both algebra and calculus arguments to the y-coordinate. Change every place there's an x to a y, and we should be good to go. Now, the reason this is sort of a profound idea that Galileo comes up with is it wasn't what people observed. In fact, people were very much aware that different objects, depending on their size and shape and maybe even the mass, they fell with different rates. And Galileo said, no, they all fall with the same rate of change of velocity, 9.8 meters per second squared. It's just some of them are subject to wind resistance. And so that picture I'm showing you on the right there is actually being done in a vacuum chamber. And you can see that it looks like a ball maybe and a feather are falling together when air is eliminated. Tomorrow in class, I'll show you another little video where astronauts went to the moon and with no atmosphere in the moon conducted the same experiment, and the rate at which a hammer and a feather fell was exactly the same. Now, of course, because it's on the moon, it's not 9.8 meters per second squared. The acceleration due to gravity on the moon is something like 1/3 of that, but still a constant acceleration for all objects in the absence of air resistance, a topic we'll address in a few weeks in the course. Now, here's my example problem, and it's the biggest thing that I think is in this pre-lecture video, and it's very similar to an example problem in your reading in Holiday Resnick Walker. I think the difference is I'm starting with 15 meters per second, and it's a different number. I think it's 12 meters per second in the example problem in the book. But I do it in a significantly more detailed manner. And I also changed the order in which I did the problem. And I used, there is not a single way to solve this problem, but I take a very rigorous kind of grind through it approach. I don't necessarily go for the quickest answer. So in any event, as you see in the picture, a person there is throwing a ball up in the air at point A with an initial velocity of 15 meters per second. The ball goes up to point B stops, and then falls back to his hand or her hand. To the person's hand at point C. And we've got some things to find. In fact, 5 different parameters. How much time does it take to reach the maximum height, which is at point B? And the problem here gives you a little hint. It says that up at B, the velocity is equal to 0. The ball actually stops up there. Now, a misconception a lot of people have is since the ball stops up there, the acceleration up there must also be 0. False. If the acceleration up there was 0, what would happen to the ball? Wouldn't it just levitate there? And in fact, it doesn't. It starts to fall. And so there must still be an acceleration of 9.8 meters per second squared downward up at point B, even though the instantaneous velocity at that point is 0. So we want to know how much time it takes to get to point B. And then we want to know how much time it takes the ball before it comes back to the person's hand at point C. Okay, with those two numbers in hand, I want to know how high it goes. What is the vertical position? I'll call that y. As I said, we're going to take our constant acceleration equations, and to every place we see an x, we're going to write a y. Okay, I want to know what is the y value at point B. And I want to know what the velocity is once it returns to the person's hand at point C. And then lastly, assuming the ball goes at least 8 meters above the person's hand, I want to know what time that is. And hopefully you can see there should be a time on the way up and a time on the way down. And here's the preliminary stuff. And I've shown you this template that I think is very valuable, particularly if you're not as strong in numeric problem solving as you might be. In fact, for some of you, I might insist on it. But you want to write down everything that's given in the problem statement. And there's more in that problem statement than just the initial velocity upward. That's certainly the most important piece. The initial velocity at point A, which we could call V0, is equal to 15 meters per second. I made it positive because it's upward. Not stated, but it is often what we choose to do by where we put the origin of our coordinate system, which you see I drew as I repeated the sketch. Not without all the detail, but I show a coordinate origin right at point A and point C. So the value for y0, the initial y position, is 0. It's also the y position at point C, isn't it? The velocity at point B, that was kind of a hint in the figure that we were given, is 0. And of course, the acceleration is, as I've been saying, 9.81 meters per second squared everywhere, and it's downward. So I made it negative. If I made upward positive for the initial velocity and the acceleration is downward, they have to have opposite signs. What we have to find: the time at point B, the time at point C, the height at point B, the velocity at point C, and the time it takes to get to 8 meters, presuming the ball goes above 8 meters in our calculation for how high it goes to point B. And of course, I've rewritten my 3 kinematics equations for constant acceleration. Equation 1, exactly the way we had equation 1 before. You'll see some people, since this is vertical, subscript the instantaneous velocity with a y and the initial velocity with a y. That's fine. Even the acceleration you can subscript with a y. And then every place there's an x in the second constant acceleration kinematics equation, I switch the x's over to y's. And then lastly, that third equation, velocity squared is equal to the initial value of velocity squared plus twice the acceleration. Of course, that's acceleration in the y direction. When we do two-dimensional problems, it'll be key to keep that straight. And then the displacement y minus y0 in the vertical direction. I think this is an important step in a lot of problems that many students neglect, and it causes them to get the problem wrong. From a practical perspective, recognize that if you get the problem wrong and you've stated all of this material up front on the first place, you're less likely to get it wrong. But there's partial credit had right here, just by writing out the things that you know to be true at all the points and formulating the problem and setting yourself up for success. And so, as we said, the problem is parametric in time. Both position and velocity depend on time. And since we want to get position and velocity at points B and C here next, let's figure out what the velocity, what the time is at position B and at position C. And so at B, you can see if I use the first constant acceleration equation, I know that the velocity at B is 0. I know what the initial velocity is. I know what the acceleration is. I don't forget that negative sign. The only thing I don't know in there is the time it takes to get to B, which, if you rearrange, is just the 15 meters per second divided by the 9.81 meters per second squared. Put that in my calculator, and I get 1.53 seconds. Now, I did the problem once numerically in my calculator, and now I go back and I do it again, this time investigating the units. And you'll see I have a meter per second in the numerator and a meter per second squared in the denominator. The 2 meters cancel. One of the seconds cancels. And so what that leaves, and I'm showing it there at the far right, is 1 divided by 1 over seconds. The reciprocal of reciprocal seconds is just seconds. If something's in the denominator of the denominator, it's really in the numerator. And so it is possible that I got this problem right because the units came out to be seconds. I see a lot of students know they're calculating time. They just run the numbers in their calculator. They get to 1.53. Since they know it's time, they just slap on seconds, put a box around it like I did. This is how you catch yourself. If you've forgotten to do something, checking the units will point out you've got a problem. And then if you've got a problem, you get an opportunity to catch it before I do. And it's even more important here when it deals with squaring time, okay? In this case, not so much because one of them cancels. But if you forget to square the time, you'll see that the acceleration, which is distance over time squared, the second squared and the second squared won't cancel, and you'll see you've got a mistake in the second constant acceleration equation. Doesn't rear its head here because our final position is 0 meters. It comes back to the person's hand at the origin. The initial y position is also 0, and so all you're left with is that 0 is equal to the initial velocity times the time to get back to the person's hand, plus 1/2 the acceleration times the time to get back to the person's hand squared. And when you put in 9.81 meter per second squared, you better remember it's downward and insert the negative sign. In order to add to 0, these two non-zero terms must have opposite signs, and that's where it comes from. I see students making a mistake where they put in minus g, and then because I had a slide earlier where g was equal to minus 9.8 meters per second squared, they negate it again, putting in a negative sign twice for the same reason. And of course, that's incorrect. As we'll study in a week, well, actually sooner than a week, signs in one-dimensional problems are really denoting direction, and the direction will become very important when we look at two-dimensional problems. In any event, if you solve for the time at point C, you'll see that it's 3.06 seconds. Again, checking units. Yep, I got 1 over seconds, which is seconds. And the interesting thing you see here is that the time to get back to the person's hands is exactly twice the time it took to get to point B. There's a symmetry to this problem since it starts and stops at the same point. And if you meet that condition, you can always make use of the fact that if you find the time to point B, you can just double it to get to point C, because points A and C are at the same spot. Or if you got the time to get to point C, you can just take 1/2 to figure out what time it was at its highest point, as long as the problem is symmetric. If it goes from the hand and then point C is down at the floor, now you've got to work the problem out in more detail. All right, armed with those two pieces of information from the previous slide, 1.53 seconds to the top, 3.06 seconds to get back to somebody's hand at point C. It's now time to find out how high the thing went. So the position, the vertical position, y at point B is equal to the initial position 0, plus the velocity initial, which is the 15 meters per second upwards. times 1.53 seconds, the time it takes to get there, minus 1/2 9.81. Why minus? Because 9.81 is downward, times the 1.53 seconds squared. Put all that in my calculator. Don't forget that negative sign. 11.5 meters, a reasonable distance. Again, done the problem once numerically. Now I check to make sure velocity, meter per second, times the time in seconds. Sure enough, that gives me meters. I have an acceleration, meter per second squared. I've remembered to square that time, so I've got seconds squared, which cancels the second squared in the denominator of meters per second squared. Sure enough, I have meters. I'm adding meters to meters. That's my first key. And then I realize that, yes, position should have units of meters. 11.5 just might be right. One thing I can guarantee you, though, if those units don't work out, I don't care what your calculator said, your answer is wrong. All right, last thing. At 3.06 seconds, twice the time it took to get to the maximum height, the object, the ball, whatever it is back in the person's hand. And so now let's look and see what the speed it's going at is as the person is catching it. What is the velocity? It's downward. So now we got to figure out the magnitude. But I think the constant acceleration equation will work this right out for us using this method. So the velocity at point C is equal to the initial velocity, the 15 meters per second upward, plus the acceleration, which is the minus 9.81 meters per second squared, times the time 3.06. If you look at it, it's plus 15 minus 30, which sure enough is equal to minus 15 meters per second, enhancing the symmetry of this problem. The ball went upwards at 15 meters per second. When it comes back down to exactly the same height, it's going minus 15 meters per second. You can use that if you have sufficient symmetry in a problem. And now the last question. 11.5 meters was the maximum height. What time is it when the ball or the object, whatever it is, reaches the 8-meter point? And so I'm using the second constant acceleration equation. Y is equal to the initial value of y plus the velocity initial times the time plus 1/2 the acceleration times the time squared. I'm putting in 8 meters for the final value y. 0 meters is the initial position, 15 meters per second, and then minus 9.81 meter per second squared for the acceleration. And you can see I have a quadratic equation in time. I've written it in the normal format, which is a constant times the time squared plus a constant times time plus a different constant is all equal to 0. You can use the quadratic formula to solve this. I have a calculator with a solve function which finds this answer very quickly for me. And I find, as you should expect for a quadratic, there are two numeric values for t. One is 0.688 seconds and the other is 2.37 seconds. And those two numbers have physical meaning. The smaller number, the 0.688 seconds, is the time it reaches 8 meters on the way up. And the 2.37 seconds is the time that the object reaches 8 meters on the way down. And so I've graphed position as a function of time and velocity as a function of time. And notice right at 1.53 seconds, that's when the velocity is 0. It stops having positive velocity because it comes to rest and starts having negative velocity, which is increasing in the negative direction. And certainly we have a parabolic curve for position, vertical position, y, as a function of time. And so the problem kind of makes sense. Everything hangs together, and there's even a chance, because the units worked out, that we got it right. And so you've been very patient working through this video, and here's the last step. And let's focus on the two curves shown on the right side. And if you look at the top one, you'll see that acceleration and time aren't constants. It increases linearly, becomes constant, and then decreases linearly. And we're going to go back to what we showed, that if the instantaneous acceleration is the derivative of velocity with respect to time, we can find the change in velocity as the integral of the acceleration over time between 2 points. And so in order to find the change in velocity, what I would need to find is the area under the acceleration versus time curve between, in this case, time 0 and time 1. And the way you would do that, of course, is with equations that you know for solving areas, like a rectangle, length times width, a triangle, 1/2 the base times the height. Now, in this case, unfortunately, there's kind of a trapezoid there on the left side, isn't there? What I would recommend you do in this case is turn the trapezoid into a second rectangle and a smaller triangle, and add those 3 pieces up, and that will give you the change in velocity. Pretty straightforward. Of course, we would have to give you in the problem adequate numeric information in order to allow you to find these 3 areas. And it's a technique we'll use for other things in the course when we don't want you to spend the time doing the calculus problem of doing a numeric integration, an analytical integration. Instead, we just want you to recognize that an integral is an area under a curve. We can do the same thing with velocity versus time. And here, in this case, the lower figure on the right, you can see that velocity is linearly increasing and then linearly decreasing. So it's not a constant acceleration problem, because if it was a constant acceleration problem, velocity would just be changing linearly the whole time. But again, just like we did before, we can find that the integral of velocity over time, in this case, is the displacement. And so all you would have to do is find the area under that curve between the points t0 and t1. If you can do that by some sum of rectangles and triangles, you would find the displacement of this object undergoing that velocity as specified in that curve. That's all I've got. We'll see you in class. If you have any questions on anything I've said in this pre-lecture video, that should be one of the first things you do. I'll call for questions, and come on with anything you got, anything I didn't explain clearly in this video. We'll address that right away. So thanks, and we'll see you in class tomorrow.